You're welcome to the continuation of TH 420, and we are now on still in group characters, but we're going to be considering a particular theorem, and we would need to recall some few things. But before then, let's note that in group representation theory, a class function is a function from a group G to any field. Particularly, we could talk about the complex numbers, but so far so good. We've noticed that we've always used the field K. Okay, so if you have a function from the group G that is to any field that is constant on each conjugacy class of G, then we have a class function. So generally, characters, like we know what a character is the sum of the diagonals of the matrix representation, right? They are all class functions. So let's note that before we begin the theorem. Okay, so the first theorem before us is today, or I think the only one we'll be doing in this video, is theorem 2.23, and it actually, I have said it as a question. It says state and prove the reciprocity theorem of Frobenius. Okay, so we're to state it and we're to prove it. And what does it state? It states that. So the statement is simply this, that if H is a subgroup of G and phi and psi are characters of H in G respectively, then the inner product, okay, of the induced character and the character of H in G, when summed over G, is same as the inner product of the character psi of H in G and the character of phi when summed over H, all in H. Okay, so that's what it says. So this is the Frobenius I beg your pardon, everyone. Reciprocity theorem of Frobenius. Okay, so you just need to be able to state this. Okay, so this is the statement. How do we prove this? So we need to recall some key things. Okay, so let me go to the next. Okay, firstly, we note that because we have an induced character here, right here, we'll need to look into the fact that whenever we're talking about the induced matrix representation, we're dealing with a subgroup H, okay, which is extended, right, to the group G, and then we write G in terms of its cosets, right? And also, because we're talking about an inner product, we need to remember that the inner product of these characters of H is same as 1 over G. Just recall from your previous videos, right? Okay, with X in G, this is phi of X, because that's phi first, and then psi of X inverse. And if you recall, when talking about conjugation, we just simply call this X with a vowel void, right? Okay, and we were able to see in our last video, the very last video, that if we take the induced character, right, and extend it to H using U, if you remember, we had something of the form psi G up there, right, because it's the induced character, to be equal to 1 over H summing over Y in G, and then we have psi of Y X Y inverse, right? Okay, so we have that. So you need to remember this too, because we'll be needing them in the proof of this reciprocity theorem of Frobenius. Okay, so let's start now with the proof. So firstly, like I said, because we have an induced character there in the first part of the first this side of it, we want to move from left to right. We'll first consider the fact that H is a subgroup of G, and that we can write G as decomposition of G into right cosets, right? And of H, and then we have the T all the way to Tn as right transversals of H and G, and so it will satisfy this equation like I'd written on the board, on the screen earlier on. Okay, so we know that Y will be UITI, and the UIs are in H, as you expect them to be, right? So as we had seen previously, we can do some manipulations that will help us with the proof. So we'll let Y be fixed and set Z to be equals to this term in here, okay? So we can find X. Interestingly, because we fixed Y, we can sum over Z, and like I said in all my previous videos, that is similar. Once you fix the Y, we can sum, and we're summing over Z, it will be the same as summing over X. So X might not need to change, it could stay the same like you saw in previous proofs, okay? So we know that because we're extending being an induced character, okay, an induced matrix representation, that if it turns out that our Z is not in H, what happens? It means the induced character will go to 0, right, of Z. Okay, so let's continue. We have the definitions in place. So now we're ready to prove. We have put our things in place. So from the left-hand side earlier on, let's look at that. In the statement of the reciprocity theorem of Frobenius, we have this here, right? So we know what the inner product of this would look like, right? So we have phi of G, psi of G actually, and then phi, summing over G, right? So we would expect something like 1 over G, right? Sum is over G, right? So we have X in G, and then we have psi G of X, and since we're using the conjugation, we have phi of X bar, right? So let's move forward and see what we have there. So that's exactly what we have here, just like I'd written. Okay, but then we know this. It's what we have here. So I just plug it in. So plugging it in, it looks something like this. So everything changes to this, right? Okay, so bringing out the factors, you have that this term comes to join this term here. So we have it together as one. The sum in X and G and over here, and that of Y is over here. So bring these two factors together. But recall we had said we're fixing Y and setting Z to be this. We're summing over Z, so it's same as summing over Z, same as summing over X. So we don't actually have to change X. We could even make it Z because it's the same thing. Okay, so that's what happened there. Oh, sorry, too much. Okay, so we were here, and we have said our Z is this now, and summing over Z and X are same, so we could just make X becomes Z and this becomes Z, right? So we have everything in place. Okay, so now we have the sum here in Y, and we know X and Z are same, right? That's why there's Z here and the Y did not change, right? Okay, so remember at the beginning of the video, we had pointed out, wanted you to note that all characters are class functions. So that's what I'm using here. So since phi is a class function, it follows that this and this term are the same, okay, because they're class functions. It doesn't change it. And the terms are independent of Y, right? Because we have fixed Y. Now, since Z is in G and the order of G, remember it has G elements. We've been using G, the degree G all this while, right? And the sum of Y is fixed. So therefore, if we're taking the sums over where Y is now, because Y is fixed, what do we definitely there'll be G of them, right? So we just multiply through by G, okay? So because when we're summing over Y here, this Y term, there'll be G of them, right? Okay, so if there are G, everything, the sum is replaced by G. So that's what we mean by multiplying through by G. So that sum has gone, you notice, and G is replacing it up in the numerator, and everything remains the same. So the G's cancel out, and we have this, right? Okay, so now note this. We had pointed out that unless X is in H, then this will not be 0. But then if Z, is not in H, then this will go to 0, right? If you recall. So we all we need to do, because our target is to show that the left-hand side of the Frobenius is going to give us this right-hand side, right? All in H, everything's in H, so we need to restrict it to H. And this is possible because, let me take us back to our screen. Okay, so because of the fact that we need to restrict all terms, we have to remove those as zeros, right? So if you remove all terms that are zeros, you definitely will be left with those that are in terms that go to zero. Those are the ones not in H, right? So those that are in H will not be zero. So we can restrict the sum to H only. That's what happens here. So we simply restrict the sum over H, and therefore you can get this to be equal to 1 over H and the sum in H of what we have here. But this is same as saying the inner product of phi of H or sum over H, and that completes the proof. Okay, so you can go over, ask questions so I could explain further if you have issues with the steps in the proof. Okay, again, these are materials you could use to do your revisions, and thank you.